So, welcome everybody. Right now on stage we have Frank Schares. He's going to talk about exploring GPU-powered backends for scikit-learn. The stage is yours.
Yep.
Thank you.
Hello everyone. Thanks to coming to the talk. So I'm Frank Schares. I'm working as a research software engineer at EuroSciPy alongside scikit-learn developers and maintainers, and I work on exploratory projects for scikit-learn. And today I am to talk about one of these projects, which is exploring GPU-powered backends for scikit-learn. Before going further, I want to mention that my work is possible thanks to, some people are coming. Yeah, I continue. I want to mention that my work is possible thanks to a partnership between the Intel Center of Excellence and the EuroSciPy. The target of this partnership is to develop and distribute computational backends that can leverage Intel hardware using the OneAPI toolchain. So we will talk about that later during the talk. It consists in a 2 times 100,000 grants that partly pays, part of which pay for one full-time engineer at EuroSciPy, which is me. So let's start with a brief introduction to GPU computing. Why do we use GPU? CPUs are more optimized for sequential computing. A GPU embeds up to thousands of small compute units, so it's more optimized for many parallel tasks. Initially, GPUs, well, the name stands for graphics processing units, so it was aimed at use case like graphics rendering, graphics computing, but the GPU architecture is also well fitted for all kinds of computing. In this case, sometimes we talk about GPU, which stands for general purpose computing on GPUs. A couple of things I want to mention. Not all parallel compute loads actually are well fitted for GPUs. You also have to look for additional conditions for this to work well. Condition being you have to have enough tasks to dispatch to saturate all the units, all the compute units on the GPU. And also you want the compute task to have some kind of homogeneity in how it accesses memory patterns, on how it runs the instructions. So not all parallel load is fitted for GPUs, but there are a lot in the scientific computing in the Python ecosystem that actually fits GPU architectures. I also want to mention that in the scientific computing, in the Python ecosystem, we mostly heard about NVIDIA GPUs on CUDA computing, but other manufacturers are pushing to enter the market. So here I mentioned AMD on Intel GPUs. When we think about bringing GPU backends to scikit-learn, we also consider how it can run on GPUs of other manufacturers. So during the talk, I try to, in particular, give some benchmarks of how it can run on Intel GPUs. Let's start with trying to highlight the performance jump that we can have on simple operation on different devices. This plot on the left, it shows wall time benchmark. The y-axis is a log scale of torch.matmul call between two square matrices of size 4000. So on my work laptop that have 4 cores, it's basically half a second to run the matrix multiplication. At the other end, with discrete server-grade GPUs, it's about 10 millisecond range, so it's a 50 times speed up. There's an interesting thing in this benchmark I want to focus on. I also managed to use the Intel backend for PyTorch to run this operation on the integrated GPU that is embedded with my laptop. It ranges in about 100 milliseconds, so it's a 5 times speed up compared to the performance on the CPU in the same laptop. I thought this cool. I don't know if it has many use cases, but I will try to give similar insights later. On the right, it's similar benchmark with similar observations, this time for torch.topk call, where we look for top 100 maximum values in a vector of 2 250 millions. Float 32, the one thing is here, we don't see that much of a performance jump for laptop iGPU or Intel server-grade GPU. That might also be because the Intel backend for PyTorch is in earlier development, so maybe it's not that well optimized yet. So that's it for an overview of GPU computing. Now, how can this be used to improve performance in scikit-learn? I'm going to talk about several strategies that are being considered, some that are being implemented already. And let's talk with the initiative that consists in leveraging the array API standard to work with arrays from other array libraries, including array libraries that have GPU support in scikit-learn. So let's not talk about scikit-learn right now, but I'm going to introduce just what is the array API standard. Let's start with a simple example. With NumPy, we import NumPy, just create some two-dimensional data, and we just take the maximum over the column. That's something pretty standard. And now, let's say we have heard there is another array library. Let's say PyTorch, we want to try it for performance reasons. We do the same thing. We create some two-dimensional data, and we take the maximum over column. So the two code snippets, it does the same thing. Just the compute backend is different. One use NumPy, the other use Torch. What we see, it's a bit bothersome, is that despite doing the same thing, on the left, numpy.max, it returns only one output on the keyword to tell on which axis we want to take the maximum. It's called axis. With Torch, we got two outputs on the keyword is called dim. So those little syntactic differences are bothersome because I cannot write the same code and just run it with whatever array library I want. And I have to refer to documentation every time I switch. That's where the array API comes into play. The goal of the array API standard is to enable us writing agnostic single source code. So I have some high-level array library operation in mind. I use the array API standard. Here I create a function that take as input some data. I don't know which type of data, but I just assume that it's array API compliant. Assuming that, it let me have a namespace that exposes some functions that the array API standard tell that I can use that, so I use that. On this function, I'm going to be able to use it either with NumPy arrays or either with Torch arrays, so this solves the issue that we had beforehand. This is a simple example. We will just take the maximum over columns. It's not super exciting. The array API standard covers a whole lot other common high-level array operations, or you can refer to the documentation to get a better idea of what is covered or what is not covered. And as far as compatibility with major array libraries go, well, there is support for array API with NumPy. NumPy runs on CPU. Also good support with QPy. QPy allocates data and runs compute on GPU. Also support through a compatibility layer that I actually use in the example called array API compat. You have with that good support for PyTorch. PyTorch is also nice because it can run on a lot of different backends, CPU, but also all GPU manufacturers on even more exotic backends. Quick mention also to DP control on DPNP that are more specialized for Intel GPUs on Dask, which is not about GPUs, but can allocate arrays on a distributed cluster and is also progressing toward array API compatibility. Okay, so let's get back to scikit-learn. How can the array API help in bringing support for other compute backend to scikit-learn? Well, scikit-learn, almost all estimators on their feed, predict method, etc., it takes NumPy array as input, and a lot of scikit-learn code only consists in NumPy calls. And some of the estimators really are just sequential calls to NumPy array operations. So if we can replace the NumPy array operations with calls that are compliant with the array API, then from NumPy support we are going to extend to NumPy support on all array libraries that have array API compatibility. So this is an example of how it has been done for the PCA estimators. The pull request has been merged already. I didn't contribute to it, I'm just telling the story. So on the left, all the NumPy call for the PCI replaced with array API compliant calls on the right. That, in particular, will make it work with, for instance, CuPy arrays or torch arrays that have been loaded on GPU. On the compute will be also dispatched on the GPU. And then you have GPU support in scikit-learn. So what are so far the estimators and the function in scikit-learn that have this kind of support? Since the last release, NumPy 1.3, support for LDA, linear discriminant analysis, has been released already. I just was talking about PCA that has been merged in the main development branch. That it will be made available in the next release. Ongoing work is also happening on other scikit-learn classifiers, transformers, etc. For instance, min-max scaler. And for more information on discussion about the roadmap on this subject, I invite you to read the issue that I've linked on this slide on the scikit-learn GitHub tracker. Okay, so great, we have our API support. We can use scikit-learn with something that is not NumPy, like CuPy, array, PyTorch, etc. How we use it, in fact, it doesn't change much for normal use, just that instead of providing a NumPy array as input here, for instance, to a PCA estimator, it could be a PyTorch array, CuPy array that have been loading on GPU. Just since it is still considered an experimental feature, if you want to use that, scikit-learn expects you beforehand to change a parameter in scikit-learn configuration. The array API dispatch parameter has to be set to true. And when you set that, the array API compliancy will be activated, and you can just use it with other inputs. What about performance? Here is a comparison. When running, here is so the y-axis in this graph is still log scale, and we compare wall time when running the PCA on a lot of data, 5 million rows, 200 features. On the left, we pass a NumPy array. On the right, we pass a PyTorch array that is loaded on GPU. And between the two, we go from 20 seconds for this PCA to half a second with the torch array on GPU, so it's about a 40 times speed up. On this particular use case, it looks interesting. If you have this use case, it's going to unlock interactive work on actually be less time consuming. I want to mention that if you have a smaller data set, let's say 10 less data, the wall time on CPU is already less than 1 second. So in this case, maybe you wouldn't have that much interest in actually leveraging the GPU compatibility here. So it's important to have this kind of order of magnitude in mind to have the good choice of backend, I think. So let's continue about the array API compliancy. Will all estimators in scikit-learn will be compatible with all array libraries? Likely not, because the usage we can do with the array API is actually a bit limited. The array API standard only covers a subset of high-level array operation. For instance, there is no support so far for things like torch.topk or torch.cdist, which is pairwise descent computation, or numpy.argpartition. So there is still ongoing discussion. Things might change, but some specific functions in some libraries that are needed sometimes to optimize or to implement something might not be available. And even if it is, it wouldn't be probably enough for some estimators that, for instance, like random forest or histogram gradient boosting trees that involve a lot of if-else conditions on nested for loops. Typically, these kind of instructions are unlikely to be implemented correctly just using array operations. So in this case, you rather want to use a lower level code. Just a moment. So because of the array API, adoption in scikit-learn does not cover optimization for all the estimators. We started to explore another way to open all estimators to alternative implementation, where the implementation would have more agency and could basically overwrite all the method in scikit-learn estimators. So we are talking basically about a plugin system in scikit-learn. Let's see a preview of what that would be for users if such a plugin system were to be released. Users would be at the same time they install scikit-learn, invited to maybe install some other packages. That would enable some compute plugin for scikit-learn, and then again we would use some configuration parameter in scikit-learn. Here it's called engine provider. If we set the name of the engine provider to the engine we want to activate, then all the calls to the compatible estimators with the engine will be routed to the implementation override that is implemented by the engine. So then the engine has full agency. It can maybe dispatch computation to CPU, GPU, distributed core, or I don't know. So what would it look like for developers, scikit-learn developers, or even third-party developers that would want to implement and provide such plugins? It would basically consist in implementing an engine class whose list of method is enforced and documented by the scikit-learn package. And then you have a registration method that enable making it available and then used by users with the workflow I'd shown before. Something that is important too is to provide, I think, for developers with tools that enable testing the plugin against existing native scikit-learn unit tests. So here we have some trick that lets you actually run a subset of scikit-learn unit tests while activating an engine that will give additional that will ensure for user that the plugin actually have consistency with the default behavior of default implementation in scikit-learn on some level of quality. If you want more information about the plugin system, you can follow the links here on read about the foundational issue where the main discussion takes place, on the pull request with the actual array API that we have been iterating on an example plugin for k-means that runs on Intel GPU that we have also been developing. I want to talk more about this plugin for k-means, but before I want to mention that we had additional goals in mind when experimenting this plugin. The first one is that we wanted to use low-level implementation to really have an idea of the performance cap that we can reach on GPU. That is not necessarily possible with high-level array operations. And also, it would be nice if we just write this low-level code once, and instead of just work on one kind of GPU, it could work with all GPUs. Such low-level toolchain that allow that, it's not unheard of. There are actually already open standard that exists for portability of low-level code. Maybe you've heard of OpenGL, of OpenCL, Vulkan. Those are open standards that are released and maintained by the Kronos group, which is basically a consortium where tech organization can synchronize an open standard about Vulkan. I want to mention that it's very successful at, in particular, bringing portability in video games on video gaming. So if it's possible with Vulkan for video game, maybe it could also be possible for scientific computing. And in particular, there is actually a standard that has been worked on that's called SYCL, which aims at just that. So it defines a standard for a C++ domain-specific language on the premises. If you write your C++ code with this language, you will have the compilers will be able to compile for a lot of different hardware, CPUs, GPUs, NVIDIA GPUs, AMD Intel GPUs, and so on. On such compilers, for the time being, it includes open source compilers, LLVM with Intel contribution, and alternatively OpenSYCL. There are also proprietary compilers, so we use the proprietary ones that are distributed under the name of the WAN-API set of software from Intel. On top of that, we use more specifically Python toolchain that is called NumBuddyPex, that is a just-in-time compiler. So we write code on Python and it's going to compile at use time into code that can be run on GPU, a bit like numba.cuda. So we jump to we take a deeper dive at the result that we have with this plugin. So it's called scikit-learn NumBuddyPex. You can have a more comprehensive README on how to install it and reproduce the results on the GitHub page. And here is a set of benchmark. The y-axis is still a log scale on a various set of combination of implementation on hardware that run the k-means, 100 iteration of k-means on 50 million rows with 14 dimensions. It's a lot of data too. We are happy to see that the k-means that we implemented with carefully crafted low-level operation actually had the best performance that we actually produced. Unfortunately, one limitation for the time being of our framework, or of the NumBuddyPex framework, was that it didn't allow us to run on other GPU, so we only have the benchmark for this one on an Intel GPU. The other implementations here are with Torch, so using high-level array operations, and it's a bit slower. I want to mention in particular that this benchmark also include timing for running our implementation on this laptop with the integrated GPU. Then again, there is about a 5 times speed up, so I think it's cool actually. A bit more information about our implementation on the NumBuddyPex dependencies. So far it only works for Intel GPUs, as I said. And I must say that the installation, having a working environment or development environment can be a bit tricky at the moment. It requires separate installation of the low-level Intel compute runtime. It's not pip installable. It's conda installable, but with custom channels. So for the time being, I feel you struggle a bit. Yeah. You can have more information about the project following our blog posts. We plan on doing further similar work around the plugin system. So exploring support for other estimators with low-level implementation, maybe next-k nearest neighbors, but also creating other plugins with other software dependencies, for instance, a plugin for CUDA that would have calls to QML. And there will be more at EuroSciPy 2023. Since tomorrow at the sprint session, I will be there, and we will try to organize a workshop for GPU programming with this kind of tooling. Thank you for attention.
So thank you so much, Frank, for your talk. Questions?
Thank you. That's very interesting. So the question is, you showed different types of GPUs, but what about the GPUs that are on Apple, those integrated on the chip?
Sorry, what?
So, there are GPUs that are integrated on the chip, like
Yes.
ARM architecture.
Yes.
Can we also benefit of running?
Well, yes, that's. I think that's one of the cool findings that we had. So the difference between integrated GPUs on what are called discrete GPUs and dedicated GPUs, that integrated GPUs are directly produced on the motherboard, and also it directly reads into the memory, the same system memory that the GPU is using, while discrete GPUs, they embed their own memory. But apart from that, the architecture is the same. On some load that can run on a discrete GPU, on a server-grade GPU, it's actually supposed to also be able to run on the laptop GPU. And for this to work, so you can see here, there is a bar for iGPU plus DPEX. And I also had well, let me go back to the slide. I also had some benchmark using Intel backend running on the iGPU on this laptop. So to install that, it's kind of experimental, but you can use the Intel extension for PyTorch. You have to compile it from source using special flag that will work for your own iGPU. You just do that, and then you install the binary. It will be Python packages, and from there you can use PyTorch, just using the keyword XPU instead of CUDA. I found it to work actually pretty reliably. The performance is not always here, but actually it works. Yeah, there is no official support for iGPU, so you really have to compile by yourself and try it. But yeah, it works.
All right, we have more time for another question.
Hi. Any reason to show results with very slow or old NVIDIA GPUs?
Not really. So yeah, you can take the benchmark with a grain of salt. Sometimes I just ran it with the GPU I could access. I would have preferred to have the benchmark on consistent GPUs. It's the same actually for the Intel benchmark. The Intel GPU, the Flex 170 that is being used here, it's a medium range GPU. The best server-grade GPU that Intel has released at the end of last year, it's called the Max Series GPU. It's supposed to be a competitor to the A100. I wanted to show results on that, but I didn't have good enough access at the time of running the benchmark, so I couldn't include it, sorry.
Okay. We have time for another short question. Okay. If not, you can just talk with Frank later.
Thank you very much.
So much for your call, for your